Okay, so in terms of all these vectors we drew, the starting point of all of them is still our origin, which is right here. So if we draw a line, a vector, from that dot to where we just created this new like child vector, that right there is going to be A minus B. We essentially went over A, and then we subtracted the B vector and walked this way. So this right here, we can call that should be a dotted line. It's not a real vector. Sorry, I shouldn't have been saying A and B. I should have been saying R and S. That's going to be R hat minus S hat. Now, if you look closely, R hat minus S hat has the same length as C. And really in vectors, all we care about is the direction and magnitude with respect to the starting point. So if we were to make the starting point of R minus S here, we can also say that this line right here, where it's a vector pointing down this way, is R minus S as well. So both of these here and here are R minus S. Okay, so now that we know that, we can now express the cosine rule. We can now express the cosine rule in terms of our vectors. So c squared, rather than being c squared, is going to be the vector R minus S squared. And a squared plus b squared, well, a squared, we know, a is the vector R. Well, technically speaking, precisely speaking, a is the length of the vector R, or the modulus of R. But we're going to write an S is also B. And then we're going to sub an R and S for here as well. It's going to be 2 times R times S times cosine theta. Now, essentially what we're going to do is just some algebraic manipulations to derive the original dot product formula. So we know how to multiply polynomials. We're just going to, rather than having variables for each polynomial dimension, we're going to have vectors. So R hat times, so we're going to multiply this out. And well, first we should know that this is going to be equal to R times S, R minus S, I mean, dot product with itself. And it's kind of intuitive, or it can be intuitive. We know that if you have just a single vector R and you're taking its modulus squared, aka its length squared, it's just going to be R dot product with itself. And that right there might not yet be intuitive to you, but one way you could think of it is, let's say, we know that R itself is a vector of, dimension 2 or 3, like it's sort of like, let's say it's dimension of 2, and it's first variable in the vector has length 3, the next one has length 4. Well, if you're to dot product this with itself, it would be, 3, 4 times 3, 4, which is going to be equal to 3 times 3 plus 4 times 4, which is equal to 9 plus 16. It's equal to 25. So we essentially get that the length squared is 25, which means that if you take the square root of that, the length itself is 5. So that's not as much as a proof per se, it's just kind of an example to show you intuitively that the length squared is equal to the dot product. It's really just a generalization of the Pythagorean theorem. Because in regular Pythagorean theorem, you have, A, B, C, they're at right angles, just like each dimension in this vector is orthogonal, it's at a right angle to each other. Orthogonal just means right angle. In 2 dimensions, we know the Pythagorean theorem is c squared equals a squared plus b squared. When we're doing this dot product thing right here, we're essentially, you can say the first dimension of the vector is a, the second dimension is b. We're essentially doing a squared, and let's make it b longer than a. We're essentially doing a squared, 3 times 3 plus 4 times 4. And we get 5. And you can generalize that to 3 or 4 dimensions. And that's really what the dot product is doing. The dot product is essentially calculating this side of the Pythagorean theorem. So the square root of the dot product is calculating the length of the hypotenuse in the Pythagorean theorem. Anyway, so we kind of shown why the square of the length of the vector is equal to the dot product of the vector with itself. So here the vector itself is, it's expressed in terms of a relationship of vectors, but that's fine. This entity itself is still one vector, so we can still dot product with itself to get, the square of the modulus, aka the length of that vector. And we're just gonna keep expanding this left side. So we know that dot products, they are associative, they're commutative, they're distributive. We're not getting the exact definitions of that, but essentially means you can do the following. You can say that you can treat these as how you would expand a regular polynomial expression, where r times r, this right here essentially expands to r hat times r hat. We're foiling these, we're multiplying these together, minus s hat times r hat. So we just multiplied that. And we're also going to do this, outer terms, minus, r hat times s hat, and minus s hat times s hat. And since dot products are associative, distributive, commutative, we can simplify these, saying 2 times r times s. These terms right here are identical. Simplify it with 2. And we have minus s squared here as well. So, and we know from this kind of, not proof right here, but we know from this rule that dot product of r times r is actually the length of r squared. So we didn't actually have to simplify here. We could have gone straight from here to here. We could have straight up just said that, yeah, I shouldn't have said squared right here, actually. I don't know if that's proper notation for dot producting. I shouldn't have done this line. But I should have kept this line as is r hat times r hat minus 2 r hat times s hat minus s hat times s hat. And we know from this rule up here that we can substitute in the length of r hat squared. Minus the length of s hat squared. And we're gonna recopy down the right side of our equation over here. And if we look, this is negative s times negative s is actually plus Negative times negative is a plus, so we're going to carry that plus sign down. So if we look, we have the same terms on both sides. Cancel them out. So what we're left with is negative 2 r hat times dot product s hat is equal to negative 2 r hat modulus of r hat, aka length, times modulus s hat times cosine theta. We can cancel out the negative 2's. And we are left with the dot product rule. R hat dot s hat is equal to length of r times length of s times cosine theta. So this right here, actually, it's pretty cool. What we're saying is we can find the dot product of two vectors. And again, the dot product is a scalar quantity, meaning it's just like just the value, like 5 or it's 7. It's not like a vector where there's like different elements in it. We can find that scalar quantity by taking two other scalar quantities, the length of each of these vectors, and a third scalar quantity, which is the angle between the two vectors. So we don't even need to know the components of each vector, to kind of just need to know these like summary attributes of them. And the relationship between these is actually really intuitive in a way. Like let's say you had two vectors, which are both on your horizontal axis. They're both on like the x-axis on a typical xy graph. And one is length, 3. And one is length 2. If you're to multiply those together, they're both going in the same direction. We're literally just on one dimension here. You would say that the resulting length is 6. So if we were to express these as two-dimensional vectors each, where this vector is its x component, or its horizontal component is 3, and its y component is 0, because it's not going it's not going the vertical direction is all. And this vector, again, is 2 in the horizontal, 0 in the vertical component. If we dot product those, we get 3 times 2 plus 0 times 0. It's kind of obvious. It's all on the horizontal dimension. But let's say we had, some vector that was still 3 lengths long, and another one that's 2 lengths long, but this one was at an angle, such that, this was like 2.7 and this was, 0.5. Those, if you do Pythagorean Theorem of that, I doubt the result ends up 3, but you get my gist of it. The result of the dot product, meaning like how much these are multiplied together in the same direction, like if you multiply the two vectors in the same direction, how much power sort of goes into that horizontal direction, the answer would be more like 5.4. And this vertical component kind of distracts away, it takes away power from the horizontal component of this vector. Now, if we look at one vertical vector and one horizontal vector, and we dot product them together to see how much in common they have nothing in common. They have no components that are with each other. So you're going to be multiplying, 0, 3 times 2, 0, and we're getting 0 plus 0 equals 0. For this one right here, again, these numbers don't really add up, but if we were to do the actual dot product, it would be more like, you could say 2.7 in the x direction, 5 in the y, dot, 2 in y, so yeah, we're gonna get 5.4 plus 0. Anyway, so what we're getting at here is when we're computing the dot product, the greater the angle between these two vectors, like here the angle, I don't know, 20 degrees or something, here the angle's 90 degrees, the greater the angle, the less the result is, the less the dot product is. Like you can think is that the most the dot product can be between a vector of 3 and 2 is length 6. As you increase this angle, those two vectors have less and less common on the horizontal dimension, and the number goes down towards 0. It's 0 when the angle is 90 degrees. So if you remember trigonometry, what is a relation that as an angle, the angle value increases from 0 degrees, that the output of calling that relation or that function, that output gets smaller, meaning like when we have 0, the output is highest, it's 1. When the angle reaches a right angle, aka 90 degrees, the output is 0. When the angle is, let's say, 20 degrees, I don't know, the output's like 0.9 or something, 0.8. And I'm sure if we were to draw another example here, where we have like 3 in this direction, 2 in this direction, the kind of amount of overlap, like this little part right here multiplied by this length, would be some number close to 0, like 1. So if you've been thinking about this, the higher that, as the angle reaches 90, the output is 0. As the angle approaches 0, the output reaches 1. The answer to that is the cosine relation. So we know that cosine of 0 is equal to 1. Cosine of 90 is equal to 1. Now we're not going to develop the whole intuition of how cosines work, but you can probably watch a video on the unit circle up there. Up there, I mean YouTube. So if you remember kind of, I guess, unit circle videos, say this is the hypotenuse. Remember this whole length right here is h cosine theta. This is h sine theta. As the angle reaches 90 degrees, as theta reaches 90 degrees, h cosine theta approaches 0. What we can think of all of these as doing, what these dot products are doing, is essentially taking the length of this one times the length of this element right here, and returning our output, our dot product. And we know that the length of this right here in terms of the hypotenuse is h cosine theta. Remember that from trig, from SOHCAHTOA, etc. And that's sort of the formula we just came out with here. The dot product of the two vectors, this multiplied by this, well, 1, it's going to equal s times a fraction of r. It's going to equal the length of s times, this part of the triangle. And if this, let's say this is r right here, it's going to be r cosine theta. It's going to be some amount less than 1 times the hypotenuse. In our case, it's going to be r cosine theta. This value at most is going to equal 1. At least it's going to equal 0. This value at most is going to equal the length of r, and at least it's going to equal 0. And this right here is going to vary between 0 and 1, dependent on the cosine value. So I hope I didn't drill you to death there. If you haven't developed intuition yet, just keep going through these examples, trying to do them from scratch. And yeah, this will help us in developing more understanding of linear algebra, which will help us with machine learning.